Hello, this is Carl Perez with Online Class 5, Section 4.5. We're going to cover complements and conditional probability today, and it's Friday, September 28th, 2012. Let me motivate again our task today by posing a question. Let's say a couple has 3 children. Let's say a couple has 3 children, and I pose you this question. Find the probability that at least one of those children is a girl. Alright? The key word here is at least one, and we're going to use the principle of complements to find probabilities of this type in the at least one situation. Alright, as we know, if I draw a simple Venn diagram here and this rectangle represents my sample space of all possible choices, well, if I've got some event A indicated by a circle in this diagram, then everything outside the circle and everything inside the rectangle we refer to as not A. And of course we know that the probability of A is then equal to 1 minus the probability of not A, our simple rule of complements. Well, let me pose this original question to you again. A couple has 3 children. What's the probability of at least one girl? Alright, well, let's think about this for a minute. If I draw the 8 outcomes, allowing any child to be of any gender in any order, and assuming boy and girl equally likely in any birth, let me make that condition. We can write down very easily all of the 8 possible outcomes. We've done this in class many times. Boy, 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 girl, boy, girl, boy, boy, girl, 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 boy, boy, girl, boy, girl, 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 boy, and girl, girl, girl. All right, clearly we have 8 outcomes. In this scenario, and in a brute force type fashion, we can ask, what's the probability of at least one girl? Well, if we list the sample space, in this simple example, we can list the sample space. Well, we can see that, well, how many of these outcomes have at least one girl? 4, 5, 6, 7. I see 7 that have at least one girl, and I think we can see that only one outcome has all boys. Well, if I embrace this diagram here, I could claim the probability of at least one girl is 1 minus the probability of no girls. Right? And of course, there's only 2 outcomes in any one slot. Well, if you got no girls, that means you got all boys. So we can easily use our rule of complements here to solve problems of this type. We're looking for at least one. In this particular case, it's going to be 1 minus the probability of all boys. Well, only one of these outcomes has all boys, so 1 minus 1/8 is, of course, 7/8. Alright, we can extend this idea to other problems where we're asking for at least one in an at least one scenario. So our general rule is going to be, well, the probability of at least one of whatever we're looking for, we can easily find by taking 1 minus the probability of none, regardless of the characteristic of interest. So let me put a nice big box around that. and suggest to you another example. Please consider example number 2 in our text on page 172. So please pause now and familiarize yourself with that example in the book, page 172, example 2. Please pause now. All right. Here we're asking for the probability of at least one defective in 100 of these Firestone tires. You may recall there was a big thing about Firestone tires being defective some years ago. Some of you may be old enough to remember that. Let's see. Let me summarize the given information. Let's see. The probability of a given tire defective, and I'll symbolize that with a capital D, is going to be 0.0003. And that is explicitly given to us. All right, if we buy 100 tires, they want us to find the probability of at least one in those 100 defective. All right, that is our goal. Let me rewrite that here. I get a little more room here. So the probability of at least one defective in 100 is going to be 1 minus the probability that none are defective, applying our general rule, our general complement rule in this at least one situation. Well, the probability that one given tire is defective is 0.003. All right, keep that in mind. All right, the statement none are defective, I can also describe that with the words all are good. All 100 of these tires are good. So if I can find the probability that all 100 tires are good, I can just subtract that from 1 to find the probability that that at least one is defective. Well, what's the probability that one is good? Well, that's going to be our 0.0003. Take that away from 1, and I get 0.9997, right? So the probability that all 100 of the tires are good, by the multiplication rule, and assuming independence of being good in any given tire, it's going to be 0.9997 raised to the 100th power. Now, of course, this is too cumbersome to do by hand, so I'll use my calculator to grind this out, and I get 0.0296. All right, 0.0296. So the probability that at least one of these tires in 100 is defective, it's about 3% or 0.0296. Okay? All right, let me grab another example out of the book. I'm going to talk about number 16 on page 176. Let me put a line here. So again, pause here. And familiarize yourself with the problem statement of number 16 on page 176. All right, here we go. It says in China, the probability of being a baby boy is 0.5845. Alright, so the probability of a boy in any single birth is 0.5845. Couples are allowed to have only one child. If relatives give birth to 5 babies, what is the probability there is at least one girl? Well, remember our general rule. The probability of at least one of anything is going to be 1 minus the probability of none. Okay. So I can say, well, we are asking for here the probability of at least one girl, right? So let me write that out. The probability of at least one girl in the 5 births is going to be 1 minus the probability of no girls in the 5 births. Well, of course, no girls means boys, right? No girls means all boys. Right? We know the probability of one boy is 0.5845. So what I can say then this subtracted quantity is really the probability of one boy raised to the 5th power, assuming independence of gender in any birth. Alright, so I'll take this quantity, the probability of all boys, subtract it from 1, punch it out on my calculator, and I get 0.932. And that is the probability we seek. So we see that when we're considering, in the large scheme of things, 5 births, well, the probability of getting at least one girl is pretty high. And that's what you might expect in real life. All right. I want to do another example out of the homework list. Please familiarize yourself with number 29 on page 177. And please pause now and read that problem statement and come back. All right, we're going to be talking about composite blood samples here, and this is actually how they do large numbers of blood tests for large groups. We are asked to find the probability that at least one in 3 tests yields a positive result for the HIV infection. All right, remember they're mixing these 3, so if any one of the 3 is positive, then the test for that group will yield a positive test. Okay? Well, by our general rule, I'll again state, the probability of at least 1 in 3 positive is 1 take away the probability that none in 3 are positive. Okay? The probability that any given test is positive is 0.1. That seems a little high to me, but we'll embrace the author's given information. And, well, that means the probability that any given test is negative is 0.9. Remember, this data is for one individual blood test. All right, back to the general rule here. The probability of at least 1 in 3 positive is going to be 1 minus the probability, well, here, if none in 3 are positive, that means all 3 are negative. And I can grind out this quantity pretty easily from the multiplication rule. And I have to remember to subtract it from 1. Well, the probability that all 3 are negative is going to be, well, the probability that any given test is negative is 0.9. And by the multiplication rule, the probability that all 3 are negative is going to be 0.9 cubed. So then the probability of at least 1 in 3 positive is going to be 1 take away this quantity. So I can punch this out on my calculator very easily. And I give you a decimal answer here. I get a 0.271. And 0.271. Alright, so we've worked out 4 examples of this at least 1 scenario. And again, just in working out the homework problems, it's always in this at least 1 scenario. The easiest way to go about these, I suppose, is to find 1 take away the probability of none. So the probability of at least 1 is 1 minus the probability of none, and research the problem statement for the quantities of interest. Alright. One more subtopic I want to talk about today is conditional probability. And the symbology for conditional probability looks something like this. The probability, and we read this as the probability of B given A. Alright, so let me write that out in words. This symbol, this group of symbols represents the probability of B given A. That's just how you read it from left to right. And this vertical bar indicates a conditional probability, and all we're doing here is we're assuming that event A has already occurred. Has occurred, and we restrict our sample space or configure our sample space accordingly. All right, let me get a new layer here. All right, I think we're okay. Oh, hang on a minute. Gotta go to the back. All right. All right. All right, here we go. Conditional probability. All right, what I'm going to do is refer to the polygraph data in our chapter problem that we are very familiar with now. We've talked about this at least 4 or 5 times in class. Well, we've got test results that are positive or negative, and we've got a condition of lying or not lying, depending on the subject chosen. And you'll recall this data, of course, and we recall that the grand sum from this group was 98. Right? So 98 people take a lie detector test. Some of them lied, some of them did not lie. The machine caught them lying, or the machine did not catch them lying, depending on the subject. Right? So let's consider this how to satisfy questions of this type. Let's say I was to ask you, find the probability, or if we randomly select one, let's not forget that. We kind of overlook that assumption many times when we probably shouldn't. I'm going to say we randomly select one of these 98 subjects. I'll say find the probability of a positive test given that the subject did indeed lie. All right, so I'm kind of shorthanding this a little bit. So if I translate that into the conditional probability syntax, we want the probability of getting a positive test respondent assuming or given, remember this vertical bar we read as the word given that the subject lied. Alright, well, if we assume that the subject lied, we've got 51 subjects to choose from. So my denominator in this probability is going to be 51 available outcomes. Now, how many of those liars actually received a positive test result? Well, we can see that 42 of those subjects were actually caught by the machine, and if I punch that out, I get a decimal response of 0.824. So lie detectors, well, assuming that you're lying, the probability of getting caught is about 82%. Seems somewhat low, and certainly you'd hope for something greater than that in a lie detector scenario. All right, similarly, find the probability that the subject lied given a positive test result. Again, I'm shorthanding this a little bit. Now notice, all I've done here is reversed the order of the events given in the conditional probability statement. In this previous example, we wanted the probability of a positive test given a liar. Now we want the probability of a liar given a positive test result. And I think we'll find that these are not commutative. These events, they're cogitating, these events are not commutative. And let's grind this out. Again, refer to the table. It's out of frame right now, but certainly it's in the book. Should be in your notes also. We're assuming the event of a positive test result has already occurred. That's what the word given means. All right, and if we assume that event has already occurred, well, how many positive tests do we have to choose from? From the table, it's the sum of the positive row. We've got 57 people out of these 98 had a positive test result. Now, assuming that's already done, what's the probability of liars within that group? And we can see that within the positive test result, we've got 42 liars. Okay? So if I grind this out, I get a decimal value of 0.737, and you can see that there is a difference in conditional probabilities depending on which order you take the events. Here I'm assuming a liar, then considering positive test result. Here I'm assuming a positive test result, then considering liars within that group. All right, I want to do 2 homework type exercises to kind of drive this home, and they both refer to this polygraph data. So please pause your video, and I want to refer to number 20 on page 176. Please pause now and familiarize yourself with this problem. All right. On page 176, number 20, it says, refer to the table 4.1, and again, the polygraph data. Assume that one of the 98 test subjects is randomly selected. Find the probability of selecting a subject with a negative test result given that the subject lied. Okay. All right, so again, we read this vertical bar just as it's the word given, and you have to refer to that polygraph data table and ask yourself, well, how many liars do we have to choose from? Well, the probability of having the number of liars is the sum of the liars column, and that's going to be 51, right? All right, now within that group, assuming that it's already occurred, how many of those liars received a negative test result? In other words, the machine did not catch them lying. Well, there's 9, right? There's 9 negative test results within the 51 liars group. And if I grind that out, I get 0.176. Okay, and that agrees with the book's answer. All right. Let's look at number 22. Also on page 176, another problem in your homework list. Well, this one has a part A and part B, and again refers to the polygraph data. Let me read the problem. Polygraph test referred to table 4-1. Find the probability of negative test result given the subject did not lie. All right, so translating that into conditional probability type symbols, we're assuming a non-liar. And within that group, we're going to ask, what's the probability of a negative test result? Well, if you look at the table, how many non-liars do we have? Well, it's the sum of the non-liar column. That's going to be 47. And how many of those non-liars received a negative test result? Well, it's going to be that 32, right? That 32 cell. If I punch this out, 32 over 47 is 0.681. Okay? Let's look at part B. And again, they're hammering home the point here that these events cannot be inverted or changed without changing the value of probability. So let me ask this then. Part B, find the probability that the subject did not lie given it's a negative test result. So we want the probability of a not liar given a negative test result. Well, it's easy enough to look at the table. We're going to assume we're picking from the negative test respondees. Assuming that event has occurred, we've got 41 respondees to choose from. And how many of those respondents did not lie? Well, it's going to be the 32 cell. Right? 32 non-liars within the negative test results. All right, notice these numbers have changed a little bit. And if I punch this out, I get 0.780. So certainly not an insignificant difference, considering all probabilities have to be between 0 and 1. All right, so we've done at least 4 examples of each, plus some motivating examples, so I think that's enough for today. I'm going to end the lecture now, and of course, please refer to the online Class 5 folder for your reading assignments and homework exercises, and also, of course, the online exam 5. That is all.